So, last class we talked about intrinsic diffusion and we derived Darken's equation, which converts the binary interdiffusion coefficients, which relates the binary interdiffusion coefficients to the intrinsic diffusion coefficients. Today we will go over how we can experimentally determine the intrinsic diffusion coefficients in binary system. In the end, I will also explain how we analyze intrinsic diffusion in multi-component systems. Let us consider a binary diffusion couple, and I am showing one concentration profile here. Let us call that of component 1. So, left terminal alloy concentration is C1 minus, right terminal alloy concentration is C1 plus, and suppose we placed some inert markers at the initial interface before the diffusion started, and after the diffusion annealing for time t, let us say the markers have shifted to position xk. This is the metanoplane position x naught here, which is the initial contact plane. Now we know we can write the intrinsic diffusion flux as J1 equal to J1 tilde minus C1 times Vk, where Vk is the velocity of the marker plane. Now out of this we know how to determine J1 tilde directly from the concentration profile. So this all we are considering at the marker position xk, because that is the only lattice plane that we are able to track, because the marker can be placed only at that plane, that is at the initial contact plane. So if we want to find out J1 tilde, that is the interdiffusion flux at xk, it will be simply 2t times the area under this curve. So it would be this area, this is basically 2t times J1 tilde, because we derived this expression J1 tilde is equal to 1 over 2t integral Ci minus to Ci at xk x minus x naught dC1. Now C1 we know at the marker plane, we know what is the concentration C1, and we need to know Vk, that is the velocity at which the marker plane is moving at the diffusion time t. Now this marker planes are usually travelling at a constant composition, and in an infinite diffusion couple we know each composition plane is moving parabolically with time. In other words, we say C is a function of x over root t, where x over root t is the Boltzmann parameter lambda. So we can also write x is equal to lambda root t. To find Vk, it is nothing but the change in distance coordinate with respect to time of the composition plane corresponding to lambda, that is C1 at xk. We can write at dou by dou t of lambda root t at the given lambda corresponding to xk, and so the lambda is constant. We can write this as lambda times 1/2 times t to power minus half, so is equal to lambda over 2 root t and if we substitute for lambda again, we get Vk is equal to x over 2t, and if x0 is my origin, then this is nothing but xk minus x0 over 2t. So by determining the position of marker plane with respect to the metanoplane, we can find out the velocity of marker or the Kirkendall velocity Vk. And so once we know J1 tilde, C1 and Vk, we can find out J1. And J1 can be written as minus d1 dou C1 by dou x. Again, the concentration gradient can be determined at xk, and so d1 at the composition corresponding to xk is nothing but minus J1 at xk divided by the gradient of concentration 1 at xk. This way we can find out d2 also, which is simply minus J2 over dou C2 by dou x, and thus we can get the intrinsic diffusion coefficients from a diffusion couple experiment. Remember, we can determine the interdiffusion coefficient at every composition that is developed within the diffusion zone, but each composition is characterized by two intrinsic diffusivities, and so we cannot do so for intrinsic diffusivities. We can determine the intrinsic diffusivities only when we can track the location of the lattice plane with the help of the markers, and so only at the marker plane we can find the intrinsic diffusivities. There are other methods which have also been proposed for determination of these intrinsic fluxes. The one of the popular methods out of this is the graphical method proposed by Hyman. I will talk about the Hyman's method here, for which we need to define something called as cumulative intrinsic flux. This is nothing but the total amount of a component crossing a particular lattice plane. So the intrinsic cumulative flux is also denoted as AI. So we can write AI is just the integral of 0 to t ji dt. Now if we solve this integral, so if we substitute for ji, so let us say we are talking of component 1, so we can write dA1 is equal to integral 0 to t, and J1 is minus d1 dou C1 by dou x dt, and this is at the composition plane corresponding to the marker plane, that is at xk, and this corresponds to a fixed value of lambda, because the markers are moving at constant composition. So at that composition d1 is constant, and so we can take this outside the integral, and dou C1 by dou x we can write as dC1 by d lambda times dou lambda by dou x, and since lambda is equal to x over root t, so we have dou lambda by dou x as 1 over root t dC1 by d lambda. So we have A1 is equal to minus d1 integral 0 to t 1 over root t times dC1 by d lambda dt. Now we know C is a function of x over root t, C is a function of lambda, and so if we convert C versus distance coordinate x profile into C versus lambda, it should be independent of time, because the lambda takes care of both x and root t, and for a given composition there is a fixed value of lambda. So C versus lambda profiles are independent of time, and so dC1 by d lambda should be independent of time at a given composition. So we can take this outside the integral, and so we can write A is equal to minus d1 times dC1 by d lambda, and integral 1 over root t should be equal to t to power minus half plus 1 divided by minus half plus 1, which should be minus 2 root t d1 times dC1 by d lambda. Again dC1 by d lambda we resubstitute as dou C1 by dou x divided by dou lambda by dou x, and that should be equal to root t times dou C1 by dou x, and so we get A1 should be equal to minus 2t times d1 times dou C1 by dou x, and this is nothing but J1, and we get the expression for AI as 2t times Ji. Now for a binary diffusion we can write A2 as, similarly we can write A2 as minus 2t times d2 times dou C2 by dou x. So if we take the ratio of A1 and A2, that should be equal to d1 by d2 times minus dou C2 by dou x over dou C2 by dou x should be equal to minus d1 by d2. So by taking the ratio of cumulative intrinsic fluxes, we get the ratio of intrinsic diffusion coefficients. So how do we go about graphically measuring this? So let's consider the concentration profile again. So we have C1 minus as the left terminal alloy concentration, C2 minus as the right terminal alloy concentration, xk is the location of the marker plane, x0 is the location of the metano plane. To get the areas, let me label these points A, B, C, D, E, F, G, H, I. We know A1 is equal to 2tJ1, which should be equal to 2t times J1 tilde minus C1 times Vk, and Vk was nothing but xk minus x0 over 2t. So we have A1 is equal to 2t J1 tilde is nothing but integral C1 minus to C1 at xk x minus x0 dC1 times C1 times xk minus x0. So in terms of the area, the first integral on the right hand side here is nothing but the area A, B, C, J, D, and for the sign of the area x minus x0 is negative and dC1 is also negative, so this should be positive. Second one, C1 times xk minus x naught. Xk minus x naught is this length and C1 is this length, and so we have this as area dj EH, let's call this P and Q, PQ GFD, and C1 is positive but xk minus x naught is negative, and so this has a negative sign. So this area, there should be a negative sign here, and with this negative sign this becomes positive. Now, based on the equation with which we obtained metanoplane, we know this area A B C E A is equal to E H I E, and so we can replace this area with area E H I E minus area D J E D plus area D J E D plus, so the second can be split as this area DJE plus DE PQD, DEH PQGFD, and so this two will get cancelled and we get this area plus this area, and so in effect if I mark this area, the shaded total area is nothing but the cumulative intrinsic diffusion flux A1 of component 1. This is basically the total amount of component 1 which has crossed this marker plane in time t. This is the Hyman's method to find cumulative intrinsic diffusion fluxes. This was about binary intrinsic diffusion. Now, if I want to evaluate ternary intrinsic diffusion coefficient, it is much more difficult because we need at least two diffusion couples which will give the marker positions at the same composition, because we will need at least two diffusion couples yielding the marker location at the same composition, which is almost not possible to obtain. But we do need the relations, between intrinsic and interdiffusion coefficients in order to relate these phenomenological coefficients to the fundamental mobilities and jump frequencies. So, let us quickly look into it. In the laboratory fixed frame, again let us work with constant molar volume. In the laboratory fixed frame, sigma J1 tilde equal to 0, and so we have only n minus 1 independent fluxes. Also, the summation of concentration gradient is 0, so we have only n minus 1 independent concentration gradients, and so we defined dij tilde n, and so we need n minus 1 square interdiffusion coefficients to define interdiffusion at a given composition. But as we have seen, for intrinsic diffusion sigma ji is not equal to 0, because we need to consider the net vacancy flow also, or the term related to JV, the vacancy flux, and so we have n independent fluxes. The constraint on gradient will still apply, and so instead of n minus 1 square we have n times n minus 1 intrinsic diffusion coefficients. And we can write Ji as minus Dij n. Again we need to treat one concentration gradient as dependent, dou Cj by dou x. So n minus 1 terms for each flux, and there will be n such fluxes. So there will be n times n minus 1 intrinsic diffusion coefficients. How do we convert one from the another? So if we write the equation for, so if we write interdiffusion flux in terms of intrinsic diffusion flux, let's say for component 1, we get J1 tilde equal to J1 plus C1 times Vk. If we take the summation over all components I equal to 1 to n on both sides, the summation of J1 tilde is equal to summation of J1 plus Vk times summation of Ci, should be summation of Ji, and summation of Ci we know is nothing but 1 over Vm, and the summation of Ji tilde should be equal to 0. So we have Vk is equal to minus Vm times sigma Ji. If we substitute back into this equation here, we get J1 tilde equal to J1 minus C1 Vm times sigma Ji, I equal to 1 to n, which is nothing but C1 times Vm is nothing but the mole fraction x1. So we can also write this as J1 minus x1 J1 minus x1 times sigma Js, and this summation is performed over all components except I is not equal to I, because I took x1 J1 out here, and this can be represented as 1 minus x1 times J1 minus x1 times Js is not equal to I. So if we substitute for all Ji's in terms of Fick's law and compare the corresponding term, we can obtain the interrelation between interdiffusion coefficients and intrinsic diffusion coefficients. I will skip the steps in between and will directly write this relation, which comes out to be Dij tilde n is equal to 1 minus xi times Dij n minus xi times dsj n, and the summation is over all s except I. And this is applicable for constant molar volume. So we can say this is the extension of Darken's equation to multi-component systems. This relation will be useful when we are converting or when we are trying to correlate our interdiffusion coefficients, which can be easily obtained, to intrinsic coefficients or to the fundamental atomic mobilities through thermodynamic factors. And these relations this kind of relations we have seen before. I would like to stop here for today. Thank you.